I want to make a comment about Joel's talk. He said that he doesn't know any recent work where foams were described in 4D TQFT. So I want to give you one recent work. So in fact, it's joined with Sungbong Chung. And Daniel Rogenkamp. And I don't know if Joel is still there or not, but here is the precise information. So, and basically the point of this work is that KLR algebras can be nicely realized as algebras of surface defects in 4D TQFT. 4D TQFT, and specifically the foams, or what mathematically we know as foams, are the surface defects. So some two-dimensional objects supported on surfaces. So the reason I want to mention is, first of all, for Joel to learn something new, and secondly, because this guy, Sungbong Chung, is graduating this coming year. So this is my great opportunity to advertise someone who you may consider hiring at either Perimeter or MPI as a next postdoc. Okay, so with this remark, I now want to go back to higher structures, and higher structures usually mean algebraic and categorical structures. So unlike yesterday, I cannot promise to you that we'll stay at the level of university calculus. This is going to be quite advanced. And if you hate algebra, if you hate categories, then this is not the right talk for you, but we'll basically have a lot of it. So what we discussed yesterday, or where we finished off, is going to be the starting point for today. And the idea was that if you have some d-dimensional TQFT, you can easily generate a lower dimensional theory by what physicists call compactification, but in math it should be considered as a version of fiber integration or push forward. So if you think again about a T-Siegel type axioms, where TQFT is supposed to be a functor that associates something, some number to, say, manifold of highest dimension, vector space to codimension 1 spaces, and so on, all the way to d-1 categories for points, then if you fix some n-dimensional manifold, and if your theory is in dimension d, then you can easily generate this theory in dimension d-n, by basically sticking this manifold as a product always. So suppose, for instance, in our applications, d is equal to 6, so we start in 6 dimensions. And suppose, like in yesterday's talk, little n is equal to 3. So then I get from, if I have this functor, then I can easily generate another one, which is going to be another 3-dimensional TQFT. Not another, just 3-dimensional, because this was in dimension 6. And 3-dimensional TQFT is supposed to associate a number to a 3 manifold. So therefore, if I, instead of the dots, have a 3 manifold here, all I do, I stick it in here as a factor, and surely now I get a 6 manifold, and of course, 6-dimensional TQFT associates number to a 6 manifold. I declare that that's what now this thing is. Now, if I want to associate a vector space as an usual 3-dimensional TQFT, to a surface, I take that surface as a factor here. Now I have a 5 manifold, and sure, this does the job. It associates a vector space to a 5 manifold. So this process of push forward or fiber integration allows us to produce a 3-dimensional TQFT. In this way, it's labeled by 3-manifold M3, and that was what was under the hood. I was hiding it from you all along yesterday, but now we'll explore this kind of structure. it is essentially dimensional reduction on topologically twisted M3. So the delicate part yesterday was that the six-dimensional theory that we care about does not allow twist on general 6 manifold. So it only allows twisting up to 5 manifolds. Basically, allowing it to be topological with respect to change of metric on space. So, for instance, if it's so here, yeah, exactly, right. So I'm going to erase it. I'm about to erase it. So this is actually the point that the six-dimensional theory does not allow twist on full 6 dimensions. It allows up to dimension 5 maximum. And as a result, what happens is you can therefore stick here anything with little n up to 5 and expect some theories, now not topological, just QFTs, labeled by topological types of manifold. In fact, it's not quite QFT, it has additional structure, so it's conformal. So I can say conformal quantum field theory. So that's a little better, but still not topological. Now, this process in physics is sometimes called 3D correspondence. So this is one name you may hear sometimes. And the reason it's called such because it starts with a 3-manifold and spits out for you a 3-dimensional QFT labeled by that 3-manifold. So the process is roughly this. You start with M3. It produces some quantum field theory, which often is called T of M3. And in discussion yesterday, this theory is described very concretely in terms of some quiver that has the same graph as our Plumbing graph of the manifold, and so on and so forth. But this is some complicated gadget which is not mathematically defined. It's good enough for physicists, but it's real theory with Lagrange and so on. And the point is that from here you can compute all other kind of things. For example, you can compute this object z hat that we discussed yesterday as a Q series, and Seiberg-Witten invariants, lots of other things. The closest to mathematical description of theory T of M3 that I know of is you can associate to it a certain modular tensor category also labeled by a 3-manifold. So for example, for Poincare sphere, you get category whose Grothendieck group is Verlinde ring of E8 at some level and so on. So this is kind of modern philosophy of this 3D correspondence and fiber integration in the context of QFTs. And like I briefly mentioned yesterday, this 6-dimensional theory is also labeled by choice of root system. So I should say that as part of the data, there is a choice of G. I think I'll think of it as a gauge group, although this is not quite correct. And therefore, the resulting theory here is also labeled by choice of 3-manifold and G. But for most of my discussion today, I'll assume it to be something like SU2. Actually, that's what I did yesterday as well. And I'll completely suppress it from notation. But if you want, the more precise version should include choice of this root system G. So in fact, all of these outcomes that factor through it, we can repeat. So this is version for 3 manifolds, but you can try to play this game and construct some QFT or Euclidean field theory from the same process by starting in 6 dimensions and trying to stick a 4-manifold in there. So then by counting that we start in 6, we do this push forward the fiber integration along 4. Whatever this is, it should be a 2-dimensional theory. And we're interested also in conformal version. But now as I briefly mentioned yesterday, we're actually in business because here analogous relation will be that starting with 4 manifold, you produce some 2D CFT. It has, maybe I should write it in notations, 2/2 CFT. Sometimes it's called T of M4. And to this, again, you can start compute various correlators, various observables in this, which what looks like physical theory, and produce, again, lots of interesting gadgets. But one of the things you can do is you can consider Q cohomology with respect to one of its supercharges and extract a structure which is basically vertex operator algebra of a left-moving sector of this theory. And you should think of this as analog of this tensor modular category for 3 manifolds. And this actually is a good approximation to the full physical theory. So in some sense, I want to put here that it's almost equals in the sense that perhaps it even determines T of M4 in all cases, so it doesn't lose too much information. And modulo some of these details related to supersymmetry and so on, which are not terribly important, the message here is that if you're talking about 2-dimensional conformal field theories, they surely have a nice mathematical description in terms of vertex algebras. And therefore, this general belief based on this existence of 6-dimensional theory tells that there should be some correspondence between 4 manifolds and vertex algebras. So again, there is always this choice of G that I'm suppressing, some root system that goes for the right. So this looks quite strange. And again, if you do this partial topological twist along 4 manifold, the result will depend only on smooth structure, but not choice of metric or other details. I mean, very detailed choice of metric. So now it becomes a very interesting topological invariant of 4 manifolds valued on vertex algebras. And it looks pretty strong. So for example, you can ask, can I reconstruct other invariants from it, like Donaldson invariants or Seiberg-Witten? And this is what we'll do in a moment. But this is kind of piece of big picture where many of the things that I'm going to tell you today come from. So in a minute, I'm going to abandon this philosophy, and I'll get back down to earth, and I'll try to do concrete computation. But I don't want us to be surprised, like yesterday in the end, where the hell it came from. I want to reveal the secret right in the beginning. So we'll see some features of this vertex algebra, even if we do something extremely traditional or rather baroque. Any questions at this point? Oh, yeah, thank you. So the question was, if 2 supersymmetries require the partition function to be constant, or if it can be something interesting. It can be actually something interesting, because more specifically, the way physicists would call this supersymmetry, I didn't want to say it, but since you asked, it's called 0,2. It's not 1,1. It means that supersymmetry lives only in the left-moving sector, holomorphic sector. So in 2 dimensions, you can parameterize everything in terms of coordinates z and z bar. And these are usually called left and right. And it's only z bar sector, or dependence, which carries whose corresponding translations carry odd supercharges. And as a result, partition function actually is nice. It basically, if you take Q cohomology or compute something which is manifestly supersymmetric, you basically kill the z-bar dependence. So it's actually our friend, not a foe. So one thing you can do, you can compute elliptic genus. So in this theories, there are again many functors that you can now, if you didn't know that it comes from a 4 manifold, if this is your starting point, you can compute some correlator or elliptic genus. And this is particular partition function, which now is going to be some nice object, holomorphic, and have only Q dependence, but say not Q bar dependence. And our question would be, for instance, what is the corresponding 4 manifold invariant? So if this 2D theory comes from a 4 manifold, then each of the things you can normally associate to a 2-dimensional CFT should also come from a 4 manifold. And that's kind of question that we want to ask. So maybe since this question came up, I'll say one more word. So if you have a 2-dimensional theory, one natural thing you can do is to compute its central charge C left or C right. Now they're different. So again, I promised you that we'll be talking about high algebraic structures and rather complicated algebraic structures. So the Virasoro symmetry that describes such CFTs, the Virasoro algebra in left and right, are not exactly equal because of this asymmetry. So there are two corresponding central extensions of that enter the Virasoro, and there are different values, C left and C right, and you can ask, how do they depend on a 4 manifold? In other words, if I now ask about these central extensions, what do they compute from the viewpoint of 4 manifold? And you can probably guess the answer, because this C left and C right are the most basic invariants of a 2-dimensional conformal theory that you can imagine. So what would be the two most basic invariants of a 4 manifold that you can imagine? Since we're supposed to be talking about 4 manifolds today, let's think of what are the basic ones. Yes, but we have two. Anything else you can think? Exactly, signature and Euler characteristic, and not so surprisingly, in case, say, where my group is fixed to be SU2, it happens that C left is one combination of chi and sigma, and C right and some other combination. So it kind of matches that two basic things about 4 manifolds match two basic things about VOAs or this theories T of M4. So in case if you care, here's explicit formula, but again, I don't think precise coefficients here matter as much as the fact that they line up nicely with corresponding invariants of 4 manifold. So that's the explicit expression. Okay. All right, so now at this point, as I promised, I want to quit philosophy and continue with completely different path. So suppose I don't like algebra, especially vertex algebra, which is not true, but I'll pretend that that's the case. And I'm very old-fashioned, conventional 4 manifold topologist, and I want to think of what kind of invariants are there. We just listed two, signature and Euler characteristic, but these are very poor. Of course, they don't distinguish many manifolds. And for sake of our discussion today, we can also assume that 4 manifold is simply connected. I don't think it's terribly necessary, but we may do that. So then, at least in that case, chi and sigma determine Betti numbers, but again, that's not good enough. So most powerful invariants that we have currently on the market, if you don't count this VOA of M4 as a well-defined object yet, come from gauge theory. So if you don't like algebra, your only other choice is to go back to gauge theory. You can consider gauge theoretic invariants, which are always modeled on the following philosophy. You write some PDEs, partial differential equations on a 4 manifold. You study their solutions. Then you ask yourself, did I find all of the solutions? Meaning you write the so-called moduli space. Then you ask yourself, is this space really a space? It usually is not. And then you ask, can I integrate over that space? You usually cannot. And if you can overcome all of these obstacles, in the end, you get kind of integral on that moduli space, which becomes your invariant. So As you can see, this involves a lot of analysis, and today we'll actually do some of this analysis quite explicitly, but admittedly in simple enough cases. So invariants that are available on the market are, say, Donaldson invariants. These are the most famous and the earliest of this type, based on simple self-duality PDE. Equivalent to them are Seiberg-Witten invariants, which are based on partial differential equations that I'll write in a second. And these are easier to study in many cases. But then there are other ones which are a bit less known, but equally complicated, if not more, as Donaldson invariant. For example, there is Waffe-Witten invariant or partition function. And one notable thing about it is that it's defined for a given four manifold and a gauge group as sum over Euler characteristics of solutions to this instanton equations Fa plus equal to 0. And cool thing is that very often this is some sort of modular object. So that's what's interesting about it. What's disturbing about it is that it's extremely hard to compute. So again, for reasons that we're going to discuss in detail. So my goal is to start with some invariants like this. And this little n. Oh, a question was, sorry, I keep forgetting it. Question that Peter asked, what is the upper index n that corresponds to the power of q? And q is the formal parameter in this generating function. So n here is the C2 of the corresponding bundle, or otherwise known as instanton. No, modular means that it depends. It's expected to be modular of some sort, but it could be, depending on circumstances, modular function, if you're lucky. It could be modular form of certain weight. It could be vector-valued modular object, or it could be mock modular. And probably these are examples which have been understood, and probably even more complicated things are allowed. So it's not quite nice and modular as we might have expected. So Seiberg-Witten invariants, which are the simplest, and they're actually the only ones until so far in the history of gauge theoretic invariants of four manifolds that can really be computed on any manifold. I want to emphasize this. It's really shocking that after all of this history, all we have is Seiberg-Witten invariants, which are based on the following equation. Gauge group is U1 abelian, and that actually helps a great deal. That's actually where they get much of the mileage. We write analogous equations as for Donaldson theory Fa plus, but the right-hand side is not 0, but rather is psi bar psi, where psi is a section of spin bundle on a four manifold. And now we have two variables, gauge connection A and psi, which is a section of spin bundle. So we need two equations. And for spinors, natural equation is Dirac equation, so that makes it into a system of Seiberg-Witten PDE. So normally, once we solve these equations, and again, question is, first of all, find one solution. It's usually hard enough. Then to ask, find all solutions, namely construct some moduli space of these solutions. And then form some sort of integral, which in this case boils down to integrating a top degree form, which is basically first Chern class of some universal bundle, and D is the dimension of Seiberg-Witten moduli space. So you call this integral Seiberg-Witten invariant of a 4-manifold, but as we saw yesterday, it actually is carrying additional data, namely choice of spin C structure. So I called it H yesterday. So today, to make things more interesting, and since we're in 4 manifolds rather than 3 manifolds, instead of H, I'll use lambda. So I just want to confuse you. And that's intention. So lambda is a class in H2, and you can think of lambda as first Chern class of your gauge bundle E. So since we're now in a billion situation, gauge bundle is just a line bundle, and lambda is that. So what's good about Seiberg-Witten system is that for generic choice of metric on a 4-manifold, this moduli space is just a collection of points if it's non-empty. And already the system can teach us a lot. I'm not going to go through details and analysis, but it suffers from reducible connections. These are the ones where in this moduli space we have basically sticky type points with U1 acting on fields psi that vanish. And it also shows something else, that if you choose non-generic metric, for example, you may want to work on a Keller manifold to make things nicer. But in this subject, making things nicer means choosing generic metric, going away from things that you may like, hyperkeller, Keller, and so on. So there are a lot of counterintuitive things going on which make it extremely hard to actually compute this moduli space. It's a fun exercise, I'm not going to do it today, to choose some nice metric on something like K3 and find that you don't get the right answer. And the reason you don't get the right answer is because you chose very special metric. So you have to be generic enough for things to work. So setting that up is a long story, but I want to now show you first example, or one simple example of going away from a nice situation where you can solve these PDEs and count their solutions and declare that this is a nice number. So I'll just make a minimal modification of these equations. Namely, I'll declare that I have several species of my spinors that carry label I. These in the literature are sometimes called multi-monopole equation. And I here runs from, let's say, 1 up to NF. So physicists like to call this N sub F for whatever reason. And you can ask again the same question, what about this moduli space? Can I solve these equations? And so on and so forth. Bundle doesn't change. But, yeah, very good, yeah. Question was, what happens to the bundle? Bundle doesn't change. We still work with just U1 theory, simply coupled to bunch of psi's. So only the right-hand side for bundle changed, and we have now many Dirac equations, of course, but that's a simplest generalization of basic Seiberg-Witten story. So two things you immediately learn. I'm going to denote this moduli space M sub NF. And you can try to repeat this, but you quickly learn that this fellow is non-compact. And like I say, this is really general feature of pretty much any gauge system except Seiberg-Witten. Seiberg-Witten PDEs are very lucky, and these are the only ones that we can handle so far on general 4-manifold. Yes, dimension is generically bigger than 1, so that's actually what I was going to do next. You can use, so these are nice elliptic PDEs, so you can compute their virtual dimension of the space of their solution using index theorems. And here you find that for this multi-monopole problem, the virtual dimension of this space, M an F on a 4 manifold with choice of spin C structure lambda depends on everything we have in our game, namely choice of number of spinners, signature of the 4 manifold, chi and sigma, just as before. So that's the explicit expression, divided by 4. So here you can recognize index of the Dirac operator. Here is the corresponding index of basically gauge and action operator. So this system was studied in the literature. It's not entirely new. In fact, equations were written shortly after Seiberg-Witten because what people try to do shortly after Seiberg-Witten, they try to write many different PDEs with different gauge group representations and so on. So this definitely is in the beginning of the list. And this system is still area of reasonably active research. So I should mention work of Jim Bryan, Richard Wentworth, more recently Andrei Haidis, including his work with Thomas Olpuski, and many others. So the challenge and the reason it's such an active area of research is because, again, this moduli space is non-compact and it's not entirely clear what to do. But to physicists, actually, it is reasonably clear, especially in recent years, because, and it should have been even in early days of the subject, because now the system has symmetry, additional symmetry, which essentially rotates this complex valued spinor fields psi I. So here, on the original system, as well as on moduli space M and F, we have an action of SUNF group that permutes this psi's, acts in a natural way, and therefore, if this moduli space is non-compact, we can ask, first of all, what is the set of the fixed points that might have been compact? And secondly, can we compute equivariant version of this integral instead of integrating on something non-compact? Directly, we can compute equivariant integral over M and F of C1 of the universal bundle to D over 2 as before, and ask what this is. Okay. So a theorem, which I'm going to sketch for you in a second, whose main purpose will be to explain what this moduli space actually looks like, says that you can compute this integral, and the answer turns out to be in the form of correlation function of various operators, Z1, Z and F, in some vertex operator algebra. Okay? So because now you're working equivariantly, you introduce corresponding equivariant parameters, which you can think of as variables in the Cartan of the maximal torus of this group whose symmetry we're studying, namely SU and F. So there are NF such equivariant parameters. This I denote Z1 through ZNF. Okay. And therefore, this integral, whatever it is, it will depend on previous choices as before, such as, for example, choice of spin C structure lambda, but it will also depend, it will be a function. So now it will depend on equivariant parameters, and they enter the answer, and claim is that it is nothing but correlator, chiral correlator in some vertex operator algebra. So if you didn't care about this VOAs and velocity and all that, you could just compute this, and this theorem can be proven in several different ways now. And you simply, again, discover it, but it helps to know where it comes from. So I'm going to erase some of the blackboards. I guess if you have questions, now is a good time to ask.
I guess questions from...
I assume that he can hear you.
Can we ask questions from here too?
Sorry, was there a question?
Can you hear us for a question?
Yeah, yes, I can hear you.
So the Sabbe-Witten theory is related to Donaldson theory for pure SU2. Is this equivariant Sabbe-Witten theory related to some equivariant Donaldson-Witten for SU2 with flavors?
Yes, you can probably relate it to SU2 with flavors, but so in fact, actually, any gauge invariant, any gauge theoretic invariant of a 4 manifold that has been computed, not just SU2 Donaldson theory, in fact, SUN Donaldson invariance with any n, turns out to be expressed in terms of Seiberg-Witten invariance, at least so far. Until so far, that's the status. And what's even more exciting is that even Waffe-Witten invariants that have been computed in concrete form so far always get re-expressed in terms of Seiberg-Witten. So I don't want you to think that Seiberg-Witten only controls rank 1. It actually controls everything.
But is equivalent?
One of the big challenges here, therefore, is to ask, do we have invariants which are strictly stronger than Seiberg-Witten?
Right.
Because in all known cases so far, everything can be re-expressed in terms of Seiberg-Witten invariant. Exactly. But in all known cases, so this gives a hope on the one hand that well, maybe I should repeat the question. I keep forgetting. So the question was, I'm going to erase Waffe-Witten partition function, which depends on Q. And the question was, how on earth single numbers, such as Seiberg-Witten, or maybe collection of numbers labeled by spin C structures, can encode the whole Q series? But as Peter alluded to yesterday, this Q series is actually determined by the first Q coefficient. So if you package them, if you package it and use some modularity properties, these packages come with coefficients which are precisely Seiberg-Witten invariant. At least that's happened in all of the cases that people computed so far. But more generally, I agree. It gives a hope that maybe Waffe-Witten partition function is an interesting invariant, but unfortunately, again, it's extremely hard to compute because of all the issues we're facing with non-compactness, singularities, and so on. So, other questions? So I'll give you a picture, maybe several pictures of of how this moduli spaces look like. So one cartoon version for this moduli space M and F, and let's assume lambda equals 0 for simplicity. It looks roughly as something where you have a singular point. So this corresponds to reducible solutions, namely solutions where psi's vanish. This is allowed in the choice where lambda is equal to 0. In fact, when lambda is equal to 0, everything can vanish and we satisfy our equations. When lambda is non-zero, of course, we cannot have gauge field 0 with non-trivial Chern class, but here we can. So that's usually a very bad singular point because we still have to divide by all gauge transformations, which do a good thing away from such reducible solutions. But unfortunately, if we keep doing it, we run into a problem here, which is precisely the singularity. The singularity is conical in simple enough cases, or generically, maybe I should say. And it's a cone which unfortunately does not terminate, extends all the way to infinity, and that's where the second typical problem with moduli spaces hits you, namely the compactness. So it's non-compact, and that's precisely the issue. The cross-section is the following. In fact, I can describe it in the following language. If you try to, the point is that if you try to solve a system of equations where you basically drop the curvature of the gauge field f. So that becomes a system of equations d slash psi I equals 0. And because fa now is equal to 0, sum over I from 1 up to nf, psi I bar equal to 0. So now the point is that as soon as you have nf greater or equal than 2, you can actually solve these two equations without even touching the gauge field. And now, if that's the case, you can easily rescale psi by any arbitrary number. So therefore, there is this infinite out. So all the solutions which go off to infinity are modeled on this solution to this system that covers non-compactness. And just as a simple example, imagine that our index theorem that I unfortunately erased, or maybe not, allows for, say, harmonic spinor to exist on a 4 manifold. If I have one such harmonic spinor, usually they come in quartets in this counting, then you can choose J, where J is this quaternion J, times that harmonic spinor, and therefore, your harmonic spinor psi and j psi will sum up to 0 in this equation. So you satisfy both this because both are harmonic, and you satisfy this because they come with a minus sign and cancel each other. So therefore, as soon as you satisfy some condition on signature that we see in the index theorem, you basically have this non-compactness in a very concrete, simple way. It's not just an abstract nonsense. You really can find the solution by feeling details of what I just said. So this is one picture of how such non-compact moduli spaces look like. Another picture, which will be more useful to us, is the following. You have several connected components. In this moduli space. So this is also a picture for same space M and F. So these different pieces are supposed to represent connected components. And now if you ask about fixed points of this SUNF action in order to compute the equivariant integral, you'll find that they basically come in collections of points. So luckily, there'll be isolated points, that's not so hard to see, on these connected components. And orientation of these connected components will induce their contribution to the integral, which we're about to do in this statement of the theorem, with weights +1, -1, and so on. In fact, such that each of these groups is by itself the same as single monopole Seiberg-Witten moduli space. And these points are precisely the points that you would be counting in analogous situation for single monopole cyber-acquittance system. So what I'm saying here is that the fixed point sets consists of different embeddings of M1, the usual cyber-acquittance moduli space, into M and F. The dimension, complex dimension of the normal bundle to each such component is easily determined by that same index theorem and is basically NF minus 1 over 8 lambda square minus sigma. The corresponding Euler number that's supposed to go in the denominator of equivariant integration. So here capital N denotes the component, the normal bundle for component I. This is going to be product over J not equal to I, Zj minus Zi to the same power, 1/8 lambda square minus sigma. And SU and F fixed points, yes. So this is picture of, so remember I mentioned that there is this group SU and F acting on this moduli space. It has equivariant parameters Zi, and what I'm computing for you, or rather sketching the computation, is how to take this equivariant integral. So its fixed points are compact. They in fact come precisely in nice packages as prescribed by usual cyber-acquittance theory. And moreover, so since they're compact, we can control their normal bundle. That's it. It's going to be a nice compact answer, which is what I'm going to write for you, namely this equivariant integral over this moduli space, or 4-manifold and a choice of spin C structure, is going to be proportional to what? Sum over I from 1 up to NF, 1 over product of J not equal to I. So these are sums over components of the fixed point set. Here you have the same Euler contribution that we just determined, Zj minus Zi, 1/8 lambda square minus sigma. And again, claim is that now this actually already has the form of a typical correlator, chiral correlator in some VOA. And you can ask, okay, what is the corresponding vertex algebra? Determine that. So even if you didn't care about vertex algebras, it basically comes out to you. Zi minus Zj came from evaluating Euler class of the normal bundle to two fixed points. So we basically ask, it's actually not hard to analyze this moduli space. And we ask, what does the normal bundle look like? What are the weights, corresponding weights with respect to this SUNF action? And I probably should have said that this particular analysis or theorem that I quoted is based on paper with Pavel Putrov and Dedushenko. So this is Pavel Putrov and Dedushenko. Where you can find more details, but it's fairly standard calculation to compute that Euler class, and it basically propagates to denominator and becomes the, yeah, exactly, yes, of maximal torus of SUNF that permutes the equal species of spinors. It's not symplectic, but that's not really important. Why? Oh, in that sense, yes, it is symplectic, although I don't want to use any structure on this. Yeah, at least locally it is. And yeah, so that's actually a good question. Yeah, locally this moduli spaces away from singularities are Keller. So what you have to do, yeah, that's a good question. So in fact, what I was hiding under the rug is the following. You actually need to introduce perturbation to these equations. That's a typical technique, usually used by Taubes and so on, to get yourself in a position which is generic enough. So then all of these fixed points will be away from singularities I'm worried about, and we can do localization and counting. Yeah, that's a good point. So otherwise, I would be conflicted to apply localization theorems to something which is bad and singular and so on. Just a tiny little bit. You basically need to know it's not that difficult because again, it happens that these fixed points are extremely nice. So at any given fixed point, essentially only one psi is non-zero, and all others are zero. So the normal bundle, therefore, is essentially described by n-1 guys. I think that's why we have somewhere n-1 for this dimension of the normal bundle, nf-. So it involves a little bit of analysis, but luckily it's simple enough analysis which never requires you to go beyond index theorems or corresponding spaces for the Dirac operator, the spaces of harmonic spinors at a certain time. Okay, I already forgot what the question was. Yeah. Okay, so maybe I want to now say a few more things. I don't want to take too much time. I'm extremely slow, but I'm glad. So I'll take 10 more minutes. Is it okay? We're doing fine on time. So first of all, to finish up this, I want to point out the following, that you basically compute this chiral correlator, that's fine, but then actually another miracle happens. You find your corresponding VOA, even if you didn't care about vertex algebras, but then you can ask exactly the same question. What if I, starting with this VOA, compute not a chiral correlator where I have various points scattered on a plane, but rather compute the corresponding character? So you work out this answer, you compute this guy, and then you surprisingly or not surprisingly discover that this is precisely the Waffe-Witten partition function of your 4-manifold and variable Q. So what this does, just like in yesterday's talk, this VOA packages completely different gauge theoretic invariants of a 4-manifold in a nice package. So they are different computations inside the same the same vertex algebra. So in this part, which was supposed to be much shorter, I did go extremely slow. I was going to demonstrate how to go from basically how vertex algebra can be useful for 4-manifolds. So it encodes certain structure, and again, different PDEs that would be completely different moduli spaces, doing completely different analysis, end up in the same VOA. So in that sense, VOA is a good umbrella for different computations there. So now, in the remaining 5-10 minutes, I want to ask a reverse question and just give you a glimpse of what can it do for VOA people. So is there something 4-manifolds offer back to that community? Because now we have a dictionary between vertex algebras and 4-manifolds, so it's natural to ask, if you have a favorite 4-manifold, what is the corresponding VOA, and vice versa? And in the spirit of yesterday, I want to ask a question about equivalences. So as we described yesterday, there are different operations on manifolds which don't change them, but change just the way we build them. So in particular, the Kirby moves. A natural question is, what are the corresponding equivalences on vertex algebras? That would be very natural in the spirit of today's talk. So I want to give you just one example of such.
Can we ask a question?
Yes?
So you've got a formula for this equivalent integral, and it seems to depend only on chi and sigma. Is that all the information that you need to write that correlation function, or is there more information?
Sorry, more information, because here I wrote proportional, and the precise statement would be that, for example, Seiberg-Witten invariants come as coefficients here as well. So it does boil down to not just chi and sigma, but smooth invariants, but unfortunately, again, rather traditional one.
Mm-hmm.
Okay, so I want to spend the last 5 minutes talking about how the Kirby moves can be used to do something interesting or something new for the purpose of vertex algebras. And one very particular Kirby move, for which I am deeply indebted to Peter, who taught me various interesting salient details of it. In fact, this work that I'm going to describe next was done precisely here at Max Planck 4 or 5 years ago. And this nice and most interesting Kirby move, the slide of a 2-handle, turns out to be some interesting triality symmetry of vertex operator algebras. So let me just spend, again, 5 minutes to tell you one cool application that goes the other way, not just from vertex algebras organizing the structure of 4 manifolds, but also the 4 manifold handle slides giving you something new in vertex algebra. So I want to talk about Grassmannians, or at least start talking about Grassmannians of k-planes in n-dimensional space. And they enjoy very nice symmetry where you can think equivalently of the same Grassmannian, basically as Grassmannian of n minus k planes in n-dimensional space by picking orthogonal complement. Okay. This equivalence can be extended to some natural bundles that live on Grassmannians. For example, each Grassmannian comes equipped with a tautological or universal bundle, I'll call it S, of those k-planes in n-dimensional space. And it also has a quotient bundle, which consists of the complement. And under this equivalence, these two bundles, they basically exchange their role. The universal bundle, or tautological bundle, becomes the dual of Q for Grassmannian of n minus k planes in n-dimensional space. And likewise, this becomes the dual of S. So these are fairly standard facts about Grassmannians. There is nothing terribly deep or mysterious about them. And moreover, so far, we only see, if you wish, a duality or relation between two sides. But it's interesting that if you pass to higher structure, you start seeing a little bit more, and a duality which relates two sides now becomes a triality relating three symmetric objects. So let me denote them by T, labeled by N1, N2, N3. Each N here is an integer. And based on these integers, we'll take a Grassmannian of n1 plus n2 minus n3 divided by 2 and 1. So these three integers should obey certain relations for this to make sense, in particular to satisfy obvious triangle inequalities where sum of the two is greater than any other one. And on top of this Grassmannian, which already looks fairly involved in terms of these ends and uneventful, I'm going to take the odd version, the shifted version of the tautological bundle, S2 plus N3, add to it odd or fermionic version, as physicists would say, of some number of copies of the quotient bundle in my notations N2. And I'm going to construct out of this geometric thing something that in vertex algebras people do quite often. I'll basically construct a chiral de Rham complex and corresponding chiral algebra. Which now, as a result, will be labeled by N1, N2, N3, which appear in this construction, in fact, in completely asymmetric way.
A pedantic comment? I think you mean CDOs, because chiral de Rham is n equals 2, commit 2?
Well, yes, I do mean CDOs. So shall I write CDO is?
Yeah. Makes me happier. Yeah.
Yes, yeah. Sorry, I wanted to write more telegraphic or more plain English notation. So the point that I'm trying to get to is that now this object is invariant under three permutations of N1, N2, N3. And this is something that, again, this higher structure buys you compared to classical duality of usual Grassmannians. And again, the point is that as far as I know, this kind of statement in terms of chiral algebras is new. And where it comes precisely from requiring that in this dictionary between vertex algebras and four manifolds, you get invariance with respect to so-called two-handle slide, very much like what we saw yesterday in the case of three manifolds. So I'll stop here.
All right, so I think we'll let Frimber people ask questions first.
Questions from more questions from us? I think we might have exhausted our questions already.
Well, is there anyone here who would like to ask? And someone asking here. The most exercise we'll ever get in that book. Yeah. No.
We don't need the mic, right?
Oh,
This mic.
okay. So, so some of their combination is related to rank that was underlined, and this whole correspondence there is. Okay, so that's one of the combination of F. The other actually has to do with the whole. So even if you ask me what is the four manifold for which is the algebra, it's not a manifold, it's a piece of manifold. Think of it as like simplex of the vertebra that participates in zero construction and that has two handles, which are species roles, But some of this N1, so basically N1 and N3 are computer packaged information. So they encode some of the topology information and the
So yesterday you had a nice theory for these graph 3 manifolds.
Well, here, you're asking what would be the corresponding UA, for example?
So for which 4 manifolds do you have?
Very few, very few. So the current constructions allow you to basically construct it out of handles one by one, but that's very slow. So with that technique, I cannot reach it on K3. I cannot tell you what's DOA for K3, which is nice format.
What is their mathematical definition? I mean, I'm not asking whether you computed precise difference.
I don't think so. Roughly speaking, it's what we're trying to ask mathematically is what is the algebraic structure that acts on moduli spaces of instant points. But that question is imprecise for a number of reasons, including and most importantly because of this compact. So making it precise in this form, I think, is cool. So another way would be to try to make sense of it. But it's also quite complicated. So I don't know, that's a good question. That's probably.
Are there any other questions? Here or on the other side?
So yesterday you mentioned that the written genus comma.
Oh yeah, so elliptic genus or written genus is for this DOA, written genus is essentially encoding information about a property.
But for what input do you get that?
So it's a correspondence. It's given a 4 manifold and a choice of keys. Get some vertex algebra. And written genus of that kind of. So the point is maybe 4 manifold invariance again factor through this group. So you start with a 4 manifold, you construct vertex algebra. And written genus of that will give you a buffer. The starting point is always important.
Do you expect to get more information than, like, for a few 4 manifolds, more than Zyberg with out of this, or do you expect it's just repackaging?
I do expect it's stronger because of the following. In some sense, from the viewpoint of algebraic structure acting on K-theory or suitable for homology, it's pretty much like category 5. So it's basically lifting it from numbers to corresponding vectors. And this is actually not just a fancy thing because of the following. So there is a vanishing in Donaldson theory and Everett. Manifolds. Any 2 manifolds with E2 plus greater than 1. Donaldson invariance, Everett invariance. So K3 connected some K3 will give you 0. And this is ridiculous because we don't expect this manifold boring. We expect a lot of information. And if you look under the hood how this vanishing theorem is proved, we see that it's proved it basically follows from a very stupid reason, very similar to this reducible solutions that first part of the part. And the corresponding moduli spaces are not 0, it's just a number. Therefore, already in that case, you can see that for vertex algebras, the vertex algebras which correspond to connect sum are just tensor products. So they don't vanish, they don't become trivial, they still retain that. But even for that's the reason I suspect that it's a better, longer. But of course, what would be really cool is to tackle some exotic structure. That we are very fun.
Do you have any other questions? Thanks, Sergey.